Hello everyone, hope everyone is doing good. In this video, I'm going to derive the shape functions of a triangular element, of a constant strain triangular element to be very specific. Now, before I get straight into the business of deriving the shape functions of a constant strain triangular element, I would like to tell you what is the goal of finite element analysis. It's just a reminder. The goal of finite element analysis is to find the values of stresses. We have to make sure that the components that we are designing, the stresses generated in those components are within the acceptable limits for all types of materials chosen and for all types of environmental conditions encountered. So that is the goal of finite element analysis. So we have to make sure that the stresses are within the acceptable limits. Now, in order to find the values of stresses, you should know the values of strains. In order to find the values of strains, you should know the values of displacements, nodal displacements to be very precise. In order to find the values of nodal displacements, you have to solve the finite element equation, which is the stiffness matrix into U matrix is equal to the force matrix. So the stiffness matrix multiplied by the displacement matrix, which is the nodal displacements matrix, is equal to the force matrix. In order to find the stiffness matrix, well, you have to know the shape functions. Okay, now the question is, what is the triangle for which we are trying to derive the shape functions? Just imagine that we have got a thin plate. Okay, I'm going to draw a thin plate now. Just imagine that I have got a thin plate. So in this structure, this is an example of a thin plate. Okay, the thickness here is very small. This thickness is very, very small. Now, when I say it is very small, all I am saying is that the thickness is small compared to the other two dimensions. Okay, the thickness is small compared to the length, and compared to the height, the thickness is small. Now, let us say that there is stuff that is acting on this particular structure, and the load that is acting on this particular structure, let me represent that by this red arrow here. So clearly you can see that loads are acting along the x direction, along the horizontal direction, and the load can also act along the vertically upward direction. Let me first put a set of coordinate axes. Okay, this is our x axis and this is our y-axis. One thing that you have to note in this physical scenario, and it is very important, the one thing that you have to note is no load is acting along the z direction. No load is acting parallel to the z direction. So this is our z direction. Clearly no load is acting parallel to the z direction. This is very important. This is very important. Now, if you want to analyze a structure like this, you can actually discretize the cross section of this particular structure into many small triangles. So what is the cross section that you are bothered about? Well, this is the cross section that you are bothered about, the one that I'm putting yellow in color, right? So that is the cross section, and you can discretize this into many small triangles. See, that's it. You can discretize this into many small triangles. I can go on doing this, but of course you are getting the logic behind it, right? So you are going to analyze the xy plane. That is important. You are actually going to analyze the xy plane. You are actually going to slice a cross section that is parallel to the xy plane. Okay? You are actually not going to analyze yz plane. You are not analyzing yz plane. You are only analyzing the xy plane. So this is the plane where you discretize into many small triangles. So Okay. What you are actually going to do is you take out one triangle. I think the triangle looks like this. And you are actually going to derive the shape functions for this particular triangle. Why do we want to derive the shape functions? Because only then you can find the stiffness matrix. Okay, only then you can find the strain displacement matrix. Only then you can find the stiffness matrix. Of course, you will also need to know the stress-strain relationship matrix. Okay. Now, this condition is called as the plane stress condition. Let me write that down for you. It is called as plane stress condition. Definitely, there should be more explanation to what plane stress condition actually is, but no load is acting perpendicular to the xy plane, right? And the thickness is going to be very small compared to the other two dimensions. Okay, so the stress along the z direction is going to be very small. For all practicable purposes, we are actually going to ignore the stress values along the z direction without incurring any serious error in mathematics. Okay, this is plane stress condition, and of course this is the triangle that we are actually going to analyze. So this is the triangle that you are actually going to analyze. This is the, so you will be actually finding the stresses of each and every triangle here. Okay, fine. Now imagine another physical scenario. This time it's I'm going to construct a dam wall. So here is the wall of the dam. Okay. Okay, this is the wall of the dam. It goes like this. One question, and here you can see that the water pressure is acting like this. The water, okay, the pressure of the water is acting in this direction. Of course, this is a two-dimensional representation of a three-dimensional situation. You have to exercise it more in your imagination. Okay, I can also put a set of coordinate axes. Okay, here we go. This is going to be our x-axis, and this is going to be our y-axis. So let me write that. This is our x-axis. This is our y-axis. Now, one question that you may be asking is, where do you think the thickness actually increases? You see that there is more material at the bottom compared to the top. One of the reasons is because the hydrostatic pressure is going to be greater at the bottom. So you want to put more material at the bottom. Okay, good. Now, what is the plane that you are actually going to analyze? Again, you are actually going to analyze this particular plane. This particular plane. Okay? You are going to take any cross section along the xy plane that is parallel to the xy plane. So clearly, this is the plane that you are actually going to analyze. Okay, I'm sorry for the poor representation, but anyway, you are getting the point, right? So this is the plane that you are actually going to analyze. So if I take out that plane and if I draw that plane separately, it looks something like this. So this is the plane that you are actually going to analyze. Okay. Even in this particular plane, if you watch it very carefully, the load is acting along the xy plane, and no load is acting perpendicular to the xy plane. So this is x-axis, this is y-axis, I'm sorry, that is y-axis, and no load is acting perpendicular to the xy plane. This is important. And the difference between the previous scenario and this scenario is that here the dimension along the z direction is highly pronounced compared to the x and y direction. The dimension along the z direction is highly pronounced compared to the x and y direction. Here, the dimension along the z direction is very small compared to the other two dimensions. Here, the dimension along the z direction is highly pronounced. So, the strain that is produced along the z direction is going to be infinitesimally small. For all practicable purposes, we are actually going to ignore the strain along the z direction without incurring any serious error in mathematics. This condition is called as the plane strain condition. It is called as the plane strain condition. Now, you will actually be discretizing this particular structure into many small triangles. Many small triangles. You can discretize the structure into many small triangles. Okay, the software will do that for you. And what you are actually going to do is take out one triangle and you are going to analyze. You are going to find the shape functions for this particular triangle so that you can find the stiffness. Once you find the stiffness matrix, you can actually solve the global finite element equation, that is K matrix into U matrix is equal to F matrix. And after solving this equation, K matrix into U matrix is equal to F matrix. See, I'm putting a flower bracket for U matrix and F matrix. It means that they are column matrices. Then you can find the nodal displacements. Once you know the nodal displacements, you can find the strains. Once you know the values of strains, you can find the stresses. And once you know the values of stresses, you can take some smart engineering decisions to find out whether the stresses are within the acceptable limits or not. Okay. Let us do the first step in deriving the shape functions of a constant strain triangular element. And it's going to be the same shape function for both plane stress condition and also for plane strain condition. Okay, please continue watching this video.